start the recording going and start getting y'all ready for the exam on Monday. And I guess everybody else is gonna. There's somebody. Garrett. See, I didn't call you Cash this time. All right. We have an exam on Monday. Y'all ready for it? All of Chapter 6. Conservation of energy and energy work principle and conservative and non-conservative forces. We've only got just a couple of little short sections right here. A couple of points to make, and then we'll start looking at reviewing any of the part of the chapter that you want to review, to look at. Be ready for Monday. Before I do start, do any of you have questions about the homework? No? All right. Well, we talked Wednesday about the conservation of energy. What we're going to look at today is how work done by non-conservative forces is equal to the change in the kinetic energy plus the change in the potential energy. Or KE1 minus KE2 plus PE1 minus PE2 minus work done by non-conservative forces should always be equal to 0. Of course, work done by non-conservative forces is generally considered. They play around with the signs. They'll say, well, it's a negative, so you're adding it. What you need to remember to keep it straight in your head is that however the kinetic energy and the potential energy of a closed system behave, if there is a net non-zero to that sum, it has to be something that was done by a non-conservative or an external force. Okay? So, you are a non-conservative force. When you push the box, you're an outside force acting on the system. You're adding energy to the system. So there will be some non-zero component to the change in kinetic energy or to the change in potential energy if you're pushing a box up a hill or if you're making it go faster. We've looked at the potential energy of gravity. That's just due to gravity is mass times the acceleration due to gravity times height, change in altitude, change in relative position in the gravity field. Because gravity is a conservative force, doesn't matter how far you move a box or a ball or whatever object in that gravity field. All that matters is how high above the initial starting point you were. Okay? That's not the only kind of potential energy. What about spring potential energy? You know that springs have a spring constant, K. Well, if you compress, and that K represents the force of the string, basically, the spring. The force of a spring is equal to minus K times the change in X. So if you compress a spring, and the K is negative, meaning that if it's always going to oppose whatever you add to it. So if you compress the spring, you move from X, it's going to push out with that force. If you stretch a spring, it's going to pull back with that force. Okay, that's how you find the spring constant of a spring. So, who has the sign-in sheet? There you go. The potential energy that's stored in a spring, if you take a spring and you stretch it and you hold it at that length, or if you compress it and you latch it in at that compressed state, will be 1/2 K, well, just call it Kx, where x is the distance from, Kx squared, where the Kx is the distance, or x is the distance from equilibrium that you have it compressed. So there is a point where the spring is not exerting force in one direction or the other, where it's just at equilibrium. That would be where you define x equals 0. So then if you move it away from that point, then you're either adding energy to the system, and it will respond by pushing in the opposite direction. That's why springs tend to oscillate. All right. What are some of the other kinds of potential energy we discussed? For those of you who were here Wednesday. There's chemical energy. There's also, what do they call it? Nuclear energy, atomic and molecular energy. Of course, thermal energy inside atoms at the atomic level is really just kinetic and potential energies. When you talk about something being heated up, all you're talking about is at the atomic level, the molecules and the atoms are vibrating much faster or over a much greater displacement. Chemical energy. Energy is stored in chemicals in the form of a chemical bond. That's physically a potential well that a charge is held in. And if you give it enough energy through chemical reaction or some catalyst, or through combustion by adding heat, you break those chemical bonds, and in breaking them, you release chemical energy. That's how your car works. You burn gasoline. And that gasoline releases chemical energy, which your engine converts into mechanical energy, which your car then converts into kinetic energy, which the local police officer converts into tax revenue. When you get a speeding ticket. It's all conservation of energy. The point is there are different kinds of energy, and it can be stored in different mechanisms and in different ways, but it can never be what? It can never be destroyed or created. There is a finite amount of energy in this universe, and it will never change. It will be converted from one form to another. It will be stored. It will be dissipated. But it can never be created or destroyed. So, let's look real quick at an example of using conservation of energy to estimate the amount of friction in a roller coaster. I'm on page 158. This is example 612. And there in the picture, in the figure 627, it shows the roller coaster. And here's the problem. It starts off, the cart starts off at rest at 40 meters above that lowest point. Okay, and we define that lowest point right there in the valley as 0. So it starts off 40 meters above that at rest. It rolls down the hill, and then it only makes it back up 25 meters up the other side of that hill before it comes to a stop. Of course, it doesn't stay stopped. It only reaches 0 for a moment as it starts rolling backwards, but we're going to look at the change in energy going from 40 meters above the 0 level and then getting back up to the 25 meters before it stops. Now, if there were no losses due to friction, does everyone understand what's happening here? If it was a frictionless roller coaster, like we like to hypothesize about, then the cart would not have stopped at 25 meters. It would have continued on all the way up to a 40-meter height where it would have come momentarily to rest, and either, if it was level at that point, it would have sat there, or if it wasn't, it would roll back down. But it would, without friction, it would continue rolling between those two 40-meter elevations infinitely, would never stop. But roller coasters are not frictionless. So while it's rolling down that hill and through that valley and back up the other hill, friction is doing work and is converting some of its internal energy into heat. And it is dissipating that energy out of the system. So it doesn't have the energy to get back up to 40 meters by the time it gets to the other side. That's what we're going to calculate now. Well, I'm just going to start over here. Can y'all see over here? Okay. So we're going to start with our initial energy is kinetic energy 1 plus potential energy 1. It's at rest, velocity is 0, so its kinetic energy 1 is 0, and its initial potential energy is the mass of the cart times gravity times 40 meters. Now, when it gets down to the very bottom of that valley, its potential energy is now 0, because that's what we've defined as 0 height. So the total kinetic energy at that point would be, this is at point 0, its kinetic energy is now 1/2 mv max squared, and its potential energy is 0. That's in the low, at the very bottom in the middle. Except there is an unknown that at that point, some of the energy has been lost. It's been converted to heat. So we don't know what the actual velocity it got to was, because we have no idea what the force of friction was at that point. Okay? But we do know that if we continue on, we're going to get to point 3, which is equal to, which gives it its kinetic energy, because we're talking at 25 meters up, it comes to a stop, its velocity goes to 0. So its kinetic energy at point 2 plus its potential energy at point 2 plus the work done by friction is equal to 0 plus the mass of the cart times gravity times 25 meters plus the work done by friction to that point. Well, now we have a value here so that we can equate to a value here. So we can write mg times 40 meters is equal to mg times 25 meters plus the work done by friction. So, mass times gravity times 40 meters minus mass times gravity times 25 meters is equal to the work done by friction, which is equal to what? The force due to friction times the distance that the cart has traveled. Okay? Remember, non-conservative forces, it matters how far you moved. It's not just about the starting and ending points. Remember, that's the difference between distance and displacement. And I told you that the reason you had to be concerned was because conservative forces only care about displacement. Non-conservative forces care about total distance. In the problem, they tell us that the car travels 400 meters along that roller coaster track before it comes to a stop at the 25-meter height. So, now we can write mg times 40 minus 25 meters is equal to the force due to friction times 400 meters. Have you noticed that I didn't just cancel out the mass on both sides in both of these whenever it was across the... If we're looking for the actual force due to friction, not just the acceleration of friction, we can't just wipe out that mass and gravity. So, what did they give us for the mass of this cart? 1,000 kilograms. All right. 1,000 kilograms times 9.8 meters per second squared times, what's 40 minus 25? 15 times 15 meters in height is equal to the force due to friction times 400 meters. So, someone with a calculator. Let's do some arithmetic. 1,000 1,000 times 9.8 times 15 equals, did you do it? No, I mean before you divide through by 400. Okay. 147,000. What is that? Kilograms, meters squared per second squared? Joules is equal to the force of friction times 400 meters. And if we divide through by the 400 meters, 367.5 joules divided by meters. Somebody? What would that be? Newtons, thank you, is equal to the force due to friction. Now, I want to point out to you something that you need to understand about this. This is an average force of friction over that 400 meters. Why can we not talk about that as though it were the instantaneous force due to friction at any point in time? What is the force due to friction? How do you calculate it? Anybody? How would you calculate the force due to friction at any moment in time, at one point in time? If you've got an object moving along a path, what is the force due to friction exerted on that object at any point in time? Exactly. It's the normal force times the coefficient of friction, kinetic in this case. Well, what's the normal force on that roller coaster? It's changing all the time. With the slope of that rail, and the slope is very steep, the normal force is very little. When it levels out at the bottom, the normal force becomes very large. So, someone might be tempted to say, well, we know that the average force of friction is this much, 367.5 newtons. So we can estimate how fast this roller coaster would be going at the bottom of that hill. And that would be a legitimate, at least first guess at how fast you might expect it to be going. But look at that hill. The force of friction coming down that hill is going to be nowhere near the average. So you're going to grossly underestimate how fast you would actually be going when you got there to the bottom. You wouldn't be getting any of those 1 or 2% errors. Anyway. So the point is that, yes, you could use this as an estimate to make guesses about how fast the thing is going at the bottom. If you had an idea of how much of the total 400 meters was involved there. But really, it's only going to be a guess, because the force of friction is not going to be this force uniformly over the whole path. That brings us to the last topic we want to cover before we start reviewing everything, and that's power. Who can tell me what power is? Say again? It's got to do with that, yeah. But it's when you talk about your car has what? How many horsepower does your car have? No, you're right, but we'll get there. How many horsepower does your car have? Do you have any idea? 200 horsepower? What does that mean? Well, that's actually where it comes from. It's what people used to think was the power output capability of an average horse. But by definition, 1 horsepower is 746 watts. Now that sounds like something that should be on a card somewhere. Maybe we should send that to Hallmark. 1 horsepower equals 746 watts. I'm looking at you, Ashley.
No, I heard the thing.
What thing?
I heard it swivel.
Oh, well, it swivels all the time. It follows me.
Yeah, I know. I just heard it swivel and my head went.
Okay. Well, I'm looking at you because I'm dropping this big, huge hint about something that someone might want to put on their index card. 1 horsepower equals 746 watts. Doesn't that sound like something that would be handy to know in a test? Or you could just remember it. That works too. 746 watts. But what is a watt? Now, if you're an electrician or if you work with electronics, a watt is voltage times current, or whatever volts are divided, times coulombs per second. But in terms of SI units, the standard definition of a watt is a joule per second. Power is defined as the work done divided by the time it took to do it. Work divided by time, or what's work? Work is joules per second. Work is energy. Energy is always measured in joules. Work is the amount of energy that was put into a system or that was dissipated from a system, or the total amount of energy that's contained in the system. But it's always measured in joules. And if you expend or if you use a joule every second, then you're using up 1 watt. Now, I think we've talked about this before. We're going to talk about it again. When you get your electric bill from the electric company, what do they bill you for? They bill you kilowatt hours, right? So they're billing you watts times time. That's because they're billing you for how much energy you've used. If you're using 1 watt, then you're using 1 joule. But if you're using it you're using 1 joule for every second. Okay? You're not just if you just have 1 joule, that's just stored energy. It's not doing anything. It's not doing work, it's just there. It's like you have 20 gallons of gasoline in your gas tank. But if you're not driving your car, you're not burning gas, you're not using any energy. You've just got that much energy stored in your gas tank. In order to bill you for energy, you have to actually use some, so they measure it in kilowatt hours. Watts times time. Because if you take a watt, which is 1 joule per second, and then you multiply it by the 1 second that you've used it for, that you burned it, then you have actually used 1 joule of energy. And that's what they can bill you for. Does that make sense? Okay. Let's put this in something else. I like the example they use here in the book because this kind of makes it a little bit easier to wrap your head around. It makes it personal. Makes it about you or the person next to you. Think about a runner. How many of you have ever watched athletes run up and down the bleachers at the football field in high school? Did your coaches ever make you do that? Your band director made you run up and down the... Oh, okay. Well, you know, I was in band. We didn't have to run up and down the bleachers. But well, let's work through the example here. The example they give us here is a 60-kilogram jogger. Runs up a flight of stairs in 4 seconds. What do we got here? 60 kilograms. Runs up a flight of stairs in 4 seconds. The vertical height of the stairs is 4.5 meters. Four seconds. Well, that is certainly not me. So, I don't know. I wasn't there.
Yeah, it was not loud, but
okay. We need to go check?
No, it's good.
All right.
I
All right. Okay, we're going to look for two things. First, we're going to estimate how much power output this jogger generated in both horsepower and watts. And then we're going to look at how much energy he used. Okay? So first, what's his power? How much power did he develop going up those stairs? Well, how much he's 60 kilograms times 4.5 meters times 9.8 meters per second squared, mass times gravity times height, is how many joules? How much energy did he add to the system? 60 times 4.5. Somebody? You got an answer? You did 60 times 4.5 times 9.8. Hold your mouth different and try it again. $26.46? There we go. 2,646 what? Joules. And he did that in 4 seconds. So what does that give you? What answers did you get? $661.5 watts. Actually, we're going to say 660 watts because we've only got 2 significant digits. I don't usually harp on those, but that's important to remember. Now, that's how much power he developed climbing those stairs, 660 watts. How much is that in horsepower? Well, it's a good thing we got that conversion factor, right? So, what do you come up with? May not round it off quite that much, but okay. Actually, no, it would be 0.90 because of the other digits. 0.90 horsepower. That's almost 1 horsepower that he had to generate to run up 4.5 meters of steps, vertical distance. We don't know what his actual distance was. That would be, the inverse tangent of the 4.5 divided by the horizontal displacement, but that's another class. How many of you can develop 1 horsepower for very long? How long could you keep running if you were generating 1 horsepower? Yeah, I'm not going to get there. So the answer for me is easy. It's 0. I'm never going to get to 1 horsepower. No, I have once upon a time when I was a little rubber people and I could bounce good, then that was a different story. But those days are over for me. Point is, no human being is going to generate 1 horsepower for very long. And this goes back to that original definition of 1 horsepower was considered the amount of power that an average horse could maintain for the whole day or whatever. So let's look instead at how much energy did this guy use? How much energy did he use to develop when he did that, when he ran up those 4.5 meters of steps? We know he developed 660 watts of power, but how much energy? How much would the electric company bill him for? How would you calculate the amount of energy he used? That's what it would be, yes. But the way you would calculate it, from here, if you have the amount of power that he developed, you just multiply it by the amount of time he developed it for. So if he ran 660 watts for 4 seconds, then you multiply 660 watts times 4 seconds, and you're right back to 2,600 joules. What if instead of doing it in 4.5 seconds, what if he'd have done it in 4.5 minutes? You know? Now, a 4-minute mile, I'm not going to do, but a 4-minute, 4.5 meters, I could probably handle that. That's a nice brisk walk, yeah. What if he had done it in 4.5 meters? What would be different? That's what I'm asking you. What would be different if he did it in 4 minutes instead of 4 seconds? Well, what's 4 times 60? 240. 240 seconds. So 2,600 joules divided by 240 seconds, that's going to be what? About 2 watts? 2.5, 3 watts? Something like that? Did you do the arithmetic? 11 watts? Okay, 11 watts. How many horsepower is that? Divide that by 746. It's like a fraction of a horse. It's like 1% of 1 horsepower. But how much energy did he burn climbing those steps in 4 minutes? He only developed 1/10 of a horsepower. He only developed 10 watts of power, but he did it for 4 minutes. So he still added 2,600 joules to the system. So why did your coach make you run up, or your band director, make you run up the stairs when he could have just had you take a leisurely stroll? Is it because he was in a hurry, he had a hot date with the biology teacher, and he needed to get y'all out of there so he could go? But why? What difference did it make? You're going to burn 2,600 joules. You're going to add 2,600 joules to the system, whether you do it in 4 seconds or 4 minutes. What changes? The only thing that changes is the amount of power you develop doing it. Now, let me ask you this. If we go to the, we considered doing this for the lab on this subject. If we went over to the NCAT building, that's 8 meters from top to bottom, and you ran it in 4 seconds, and I ran it in 4 minutes. Which one of us is going to be more exhausted when we get to the top? And if you say me, I'm throwing a marker at you. Okay? Of course, you're going to be more exhausted, because this 2,600 joules is not the total energy that you put into it. This is why they tell you that you want to get healthy, you don't have to run a marathon, you don't have to run a 4-minute mile. All you got to do is go out and walk. You will burn energy, and you will. You'll burn that same 2,600 joules. You'll just spend 4 minutes doing it instead of 4 seconds doing it. But it's not all the energy you're going to burn. When you do it in 4 seconds, you get hot. You actually get physically hot. You get heated up and you start to sweat and perspire, and then you get mad at me when I show up 3 minutes and 56 seconds later, go, nice and cool, and I'm not sweating up my shirt or nothing. I'm not even hardly winded. We both burned the 2,600 joules getting up the steps. You burned a lot more raising your body temperature, turning it into heat. You used up a lot more. Human beings, like all other machines, are not perfectly efficient. Okay? So, when you climb those steps, you don't just put energy into working against the gravity field. You dissipate energy. Like I said, you are not a non-conservative force. You dissipate energy in generating heat and oxidizing and creating chemical reactions, and you're aerating your blood cells, and you're pumping in oxygen, and you're using oxygen, and you're burning calories and using food, all that chemical energy that you've stored. I'm not using near as much to burn those same 2,600 joules of potential energy. There's one more example they look at. It's an example of a car, and we're not going to work through the arithmetic because I want to give some time for y'all to ask questions. It's example 614. Talks about the amount of power and energy, the power needs of a car to accelerate up a 10-degree incline, or not accelerate, but to maintain a constant speed going up a 10-degree slope, as opposed to the amount of power it would need to develop if it were going to pass another car on a flat road. And it's an interesting exercise if you want to. I recommend you go and you look at it. But right now, I want to open up the floor to any questions that y'all might have from anything in chapter 6. Any of your homework assignments, problems that gave you pause that you didn't quite grasp. Because the exam on Monday is going to cover all of chapter 6. Work done by a constant force. Remember the example we talked about with the hypothetical of pushing a box across the floor? And I get it started and then I just keep pushing it without accelerating at a constant speed the whole way from there to here. How much work did I do? I did the work of that, the amount of force that I was applying to it, times the distance. What was the total work done on the box? This is a question that you're going to need to be ready to answer on Monday. Yeah. Gravity pushing down, the normal force of the floor pushing up, the motion, the vertical motion is zero. It stays at the same height the whole way. So the work done vertically is zero. What about horizontally? Total work done on the box. Exactly. Very good. The total work done on the box, neglecting the little bit of work I had to do to get it started at the very beginning. But once it was started, and all I'm doing is maintaining a constant speed without acceleration, the total work that I do is force times the distance in that direction. The total work on the box is zero because I'm applying a force times the distance, but there's no acceleration. No change in velocity means no change in kinetic energy. That means that the work that I did was exactly equal and opposite to the force that the work done by friction in the opposite direction. Does that make sense to you now? It's an important concept to understand. The work done, the change in kinetic energy plus the change in potential energy is equal to the total net work done on the system. If there's no change in potential and no change in kinetic, then all of the work that was done was what kind? Non-conservative. Conservative forces produce work done by conservative forces produce will change kinetic energy and potential energy. And they'll change back and forth. You start off with something up a hill, it has lots of potential energy. If it's at rest, it has no kinetic energy. You let it roll down the hill, and ignoring friction, the total potential energy it had at the top has to be the total kinetic energy at the bottom, unless you know how much was lost due to friction. Then you subtract that, and what's left is how much kinetic energy it has. That's it, and that is conservation of energy in a nutshell. Y'all remember about work done by a varying force? Looking at a spring. What is the kinetic energy? What is the potential energy of a spring? 1/2 kx squared. If you compress it through x meters from equilibrium, the potential energy stored in that spring is 1/2 the spring constant times the displacement squared. And if you release it and let it push a ball or a box, then it will convert into kinetic energy. And what will actually happen with a spring is, if you could get it in a frictionless environment, you attach a ball to the end of the spring, you push it back to some displacement of stored potential spring energy, and you let it go, then it's going to have that maximum, that much kinetic energy when it gets back to zero, x equals 0, and then it will use its kinetic energy to stretch the spring out till it has all of that kinetic energy converted back into spring potential energy, and it will sit there and oscillate back and forth indefinitely, as if there's no frictional losses. Just like letting a ball roll from a hill or a track, roll down. It'll get to its maximum kinetic energy at the bottom, and then it'll turn it back into potential energy, and it'll just keep rolling back and forth indefinitely if you ignore frictional losses. Any questions? Because when next we meet, it will be with an exam in hand. So, okay, well, if y'all come up with any questions, you know where my office is, you know my office number.
No card here.
Yeah, always. Index card, standard size, both sides, right on the edges if you want. You can read it. You just can't split it in the middle and use the two inside. You can't write anywhere on the inside of the card. Say again? Monday. You're asking when the exam is next week? Yeah, it's on Monday. Monday morning. Bright and early. Oh, I have no idea. Looks good.
Okay, because I'm going to transfer them to an card when I get back.
Okay.
It's easier for me to take notes on my phone.
That's fine. I don't care. If that works for you, but go through the book, through chapter 6.
That's what I did the last few times, and then I always forget to write something down. That's why I was asking. Okay. That's what I did the last time, and I was just like...
Well, you should be able to look at it and recognize the parts that I talked about. And so good.